Okay, today we're going to talk about a way to determine an unknown concentration of a solution. So let's say we have a solution and we don't know what its concentration is. Maybe we're in quality control for a company. Maybe we're just a consumer that wants to know how concentrated something is. Maybe we're working in a lab and we're making up multiple solutions, and maybe someone didn't label something, and we just need to know how concentrated that solution is for whatever our purpose is. Now, to do that, one technique we can use is called Beer's Law. Okay, we're going to use Beer's Law and use it as in a laboratory setting. So what Beer's Law tells us is that if we pass a beam of light through a translucent solution, so it has to have some color to it, the amount of light that passes through is going to be proportional to how concentrated it is. Okay, so that colored solution is going to absorb some wavelengths of light and it's going to transmit some others. Okay, so the higher the concentration that we have of our solution, the more light it's going to absorb at a specific wavelength. The lower that concentration, the less light it's going to absorb. And it's just a direct proportionality. So it's a really simple relationship. Basically what we're saying is that the colored solution gets darker, okay? And you pass light through it, that darker solution is darker because it's absorbing more light, all right? Now we graph that relationship, and when we graph that relationship, we then can use that graphical data to solve for any unknown concentrations of the same solute, okay? So what we basically do is we use a cuvette, these square-looking kind of test tube things, send a beam of light through your solution. That solution absorbs some of the light and it transmits some. And then there's a sensor over here that's going to see that transmission. Now, a quick calculation can go from transmitted to absorbed because we want to graph absorbed. And if we do that, we can collect data like you see down here, and we can build a best fit line, all right? Now I'm going to switch over to our actual Vernier program because I've inputted the same data. So here we see it. So here's the actual data that was inputted. We took the concentration, so we'd have to know the concentration of several solutions, and then we'd have to use a device called a colorimeter to pass the beam of light through and see the sensor and record the absorptions that are given from that, okay? If we do this particular solution, what we made up, here's what we get for data. You notice how it's not perfect line because it's real data. It's not just some fake computer generated stuff. And if we apply a curve fit to that, and we would definitely want it to be linear, we see that we get a really nice linear regression. Not all the dots touch the line. That's important because we don't want to try to find unknown concentrations and just say, well, I'm just going to find rise over run of this and then use that to find a line equation, or just this one, because the slope from this dot to this dot is definitely very different than from here to here. So it's the combination of all the data that we want to have, okay? If we do that and we find that slope, it ends up being this, y equals 0.009034 plus 0.04385, okay? Now that we know this line equation, all concentrations of this solute will follow that line, which means as long as we can find the absorption of anything that we make, we can plug it into this equation and we can find the concentration of it, okay? So we want to be able to track along this line as we do that, all right? Let me show you one more thing using a Fed animation. So here's a Fed animation, and we'll notice how down here, if we have zero concentration, the beam of light passes through the cuvette and we get no absorption. As I increase that beam, if we keep the sensor running, we change that absorption. So now at 110 millimoles of concentration, it's 0.56. If I go up to 160, it's 0.81. If I go up to 235, it's 1.19. So the absorption keeps increasing because this keeps getting darker. It's absorbing more and more light. And we even can visually see that beam here is not nearly as predominant as this color is over here. So it's absorbing some of that light, and then the sensor hits it. We'll probably do this in lab if we get that opportunity this year. And you'll get a chance to actually track this yourselves. So using this kind of technique, we can build this kind of data, which then allows us to solve problems like this, okay? Where we ask the question, okay, what is the concentration of an unknown solution if the absorbance is measured to be 1.05, okay? For us to answer this, we would have to have done this work ahead of time. We would have to have input the data and have a best fit line and a line equation. So this has all been done for us as part of our presentation today. And now it's our job to solve it, okay? So going to solve it now, let's go into our actual, our iPad here. and we'll take a look at what we know and we don't know in terms of our stuff, and that's going to allow us to figure this out, okay? So first thing we know that we have our line equation right here, and that equation is going to be used. Y is our absorbance, and X is our concentration, okay? So we want to make sure that we plug in Y, the absorbance for Y. So that was our 1.05. So as I plug that in, we'll take a look, and we have 1.05 as our absorbance. And now I'm trying to solve for X here, trying to figure out what this X value is here. So I'm going to subtract both sides by 0.04385. Okay? And then once I do that, I'm going to divide both sides by the 0.009034, and I'm just solving for X. Okay? So this is a pretty simple algebraic problem that you guys have done before with linear regressions. And if we solve that, we get to an answer of 111.4 micromolarity, that equals our X. So that basically equals our concentration. Okay? So again, we're just using this line equation to make this solution for this. Okay? Now, last thing, every single solute has a different line. So this is not the same equation for everything. So if we would go back to our FET animation, if we change this to potassium permanganate, notice how the numbers change. If we change this to copper sulfate, see how the number changes. You change this to nickel chloride, it changes. You change this to potassium dichromate, it changes. So not only does every line or data set change, the actual wavelength of light that we use to find this also changes, okay? So I just mentioned that because I don't want you to think that we use this equation for every single one. We had to build the equation based off of our linear regression from data we collect for every time we do this, okay? But Beer's law is pretty powerful because it allows us to find an unknown concentration by simply passing beams of light and reading the amount of light that gets transmitted, all right? Thank you.